Hi, my name's Luke, and I'm a tutor for 24HourAnswers.com. This is the first video in a series designed to help students understand the basic concepts of physics a little bit better. To give you a little bit of background about myself before we get started, I have been a physics teacher in Georgia for the last 4 years. Now this video series is going to focus mainly on problem solving, not on vocabulary and understanding concepts, but actually using those concepts to solve problems. With that said, I need to start out with just two very basic terms, scalars and vectors, and what they are, define them, and actually work a few problems with them before we move forward. So let's go ahead and jump into that. Scalars and vectors. Now, a scalar is simply just a number, okay, or a magnitude. So, just a number. Vectors, on the other hand, are a number, your physics teacher might say, like I said, magnitude. It's a number with a direction. With a direction, okay? So a scalar might be something like 3 meters, no direction on it, it's just 3 meters. It could be left, it could be right, up, down, north, south, any direction at all, where a vector is going to be something like 3 meters north. All right, so now let's go over some terms and actually differentiate between them and tell you which one's a scalar and which one's a vector. Distance and displacement. Now, distance is something that you know. It's just how far you're going, right? How far you've gone. So, for example, what we just talked about, 3 meters. Displacement is different. Okay, displacement actually has a direction with it. So 3 meters, and we'll stick with what we had, 3 meters north. Okay, meaning that displacement is a vector and distance is a scalar. Okay, now let's talk about speed and velocity. Speed's something that you're very familiar with, right? Speed is how fast you are traveling, right? So maybe 3.5 meters per second, and it doesn't give a direction to it. 3.5 meters per second, thus it's a scalar, where velocity is a vector, meaning that it's going to actually have to have a direction on it, 3.5 meters per second. And instead of giving north or south, let me give a different way to do direction. It's a little et symbol, so 3.5 meters per second at 32 degrees. Okay, so there's an angle that could be associated with it to give a direction. Finally, acceleration. Now, acceleration doesn't really have a partner like the other guys. It is just a vector. So it might be something like 4.9 meters per second squared, and we'll use south, okay, to add a direction to that, thus a vector. Another word of warning on this, kind of a trick that you'll see sometimes. Another way to make a vector is to give a sign out in front. In other words, this could be -3 meters, and that would be a vector also, or a positive sign out in front. +3 meters. That would be a vector, a displacement there, because these signs out in front of it. I'm sorry for the little equal sign looking thing. Let's circle it instead. These signs out in front here are trying to indicate a direction. Negative generally implies backwards, and positive generally implies forward. On the other hand, if there's nothing out in front, then it has to be a scalar. There is no implied direction at all. All right, so now let's work a couple of problems with displacement. Now, a note about solving problems here. I'm going to use correct significant figures throughout my problems, but I'm not going to discuss how I'm getting at it. That's just a simple concept. Please make sure to review that with your teacher. I might end up producing a video later on to try to address that. Problem solving also, I'm going to produce another video that will go over basic problem solving skills, but the first thing that I need to tell you is draw a picture. Read the problem carefully and draw a picture of what's going on. It doesn't matter how terrible of a drawer you are or anything else, you're going to see that I am just a wretched drawer. We're dealing with kangaroos, so let me make a kangaroo here, or something that looks kind of like a kangaroo, kind of big floppy ears. Sure, why not? There's my kangaroo. It doesn't matter how terrible your drawings are. What matters is trying to get a feel for what's going on in the problem. Don't worry about making them perfectly to scale. Get them close just to get the idea. So a kangaroo hops 250 meters towards a local watering hole. So somewhere over here, I'm going to have myself a watering hole, right? and he's going to go 250 meters towards it. So he's going to come this way 250 meters, right? Then he hops back, it says, change colors, he hops back the direction he came 100 meters. Be careful of directions too. So after he gets there, he's going to come back 100 meters. What was the kangaroo's displacement? Now, displacement is from start to finish. It's how far you travel, net distance. In other words, displacement here, how far he actually has gone, is this distance right here. Here's his displacement, okay? And I'm going to use the letter S there for displacement, okay? The total distance he's gone in that time. So this is just a very simple algebra problem now that we have it all drawn out, right? This is just 250 minus 100, which is going to give us 150 meters. All right, let's work another problem. A little bit more difficult, but still not that bad. An airplane flies 230 kilometers due east, but a crosswind pushes it off course 56 kilometers, 56.0 kilometers south. What is the plane's displacement? So start out and draw yourself a picture, and you'll hear me say this a few times. And so here you go again. Don't worry about things that don't matter that much. Focus on the problem solving. Draw yourself a picture to try to get a scale for what's going on, but don't worry about how good it is. So there's my plane. It's terrible. I end up using planes a decent bit in my classroom, and my students love to make fun of me for it, and so it's all good. All right, so we're going to have our plane go 230 kilometers due east. So let me draw that out. It goes 230 kilometers due east, but a crosswind pushes it off course 56.0 kilometers south. So I got 56.0 kilometers that way. What is the plane's displacement? All right, now displacement, remember, is direct line distance from start to finish. So that means the displacement here is going to be from where the plane started to where it would have finished. Okay, and this is saying that the plane, it's almost as if the plane went straight across and the wind pushed it straight down. That's the exact same thing as the wind acting over time to give me this displacement, what I will label S. Okay. Now, as you can see from our drawing, this is why it's critical to draw a picture. It makes things a little bit more obvious. This is just a nice little right triangle. So I can solve for S, our displacement, by using Pythagorean theorem. A squared plus B squared equals C squared. So 230 squared plus 56.0 squared is going to be my hypotenuse, C squared. All right, so now this is just algebra, so since all the numbers are already on the left-hand side here, punching that stuff into a calculator, I get 56,036 equals C squared. Now take the square root of both sides, and you come out with 237 kilometers. Make sure to use the units, the same units that you were given in the problem. Be careful with your units there. Lastly, let me talk about a type of problem that physics teachers like myself like to give, just because it tests a student's understanding of the definition of displacement so well. It'll go something like this. A student starts out at home, so here's home over here. It starts out in the morning and is going to go to school. So now let me draw school a little ways away, somewhere over here. Perfect. All right, so there's school. The student starts out from home, and I, as a teacher, would say, you know, they'd go this way for a little while, and I'd give the times. I'd go this way for a little while, and I'd give the times or the distances, and they arrive at school. And then they spend X amount of time at school and doing yada yada, and they go all around and everything else. And then at the end of the day, they decide they're going to take a different route back home. So they come something like this, and I'd give distances, I'd give times, and they come like this and make a stop at their local, their favorite restaurant, and then they come all the way back home. And then I'd ask, what is their displacement? In hopes that the student would do something like this. I've given distances for all these pieces. right? I gave it for this and this and this and this and this. And so my hope is that they're going to realize they don't have to add all of those up. They don't have to try to create right triangles, all of them, and use Pythagorean theorem or any other complicated method to try to get it all right. Instead, they can realize simply that the student started and ended in the exact same place at home. So remember, displacement is direct line distance from where you start to where you end, and so if you start and end in the exact same place, your displacement is just simply 0. Thank you for watching. I hope that you found this video was very helpful in assisting you to understand vectors and scalars and displacement and get some of those basic ideas sorted out. I'll be continuing with this video series, going more and more in depth and more complex as we go, hoping to try to work with you through your physics class. Remember, if you ever need any assistance or if you need some homework help or live tutoring, check out 24houranswers.com. There's a lot of great tutors, highly qualified there to help you out.